So the essence of section 1.1 is the connection between augmented matrices and linear systems of equations, and also the elementary row operations that we can perform on augmented matrices, which helps us uncover the solutions to the underlying linear system. One of the problems that people quickly run into when they start playing around with these linear systems is that sometimes it's not always obvious which elementary row operations you should perform. That's what section 1.2 is about. The Gauss-Jordan elimination method presents you with an algorithm that you can use to ensure that you can systematically go from any linear system to its solution set if you just follow the process. And that's quite handy to have. So that's what we're going to talk about now. So we're going to start by considering a very specific situation to motivate an idea. So let's suppose I had the following augmented matrix corresponding to a linear system of 3 equations and 3 variables. So you can see that I've written down just that. That's an augmented matrix of a linear system with 3 equations and 3 variables. Well, what would this correspond to? Well, remember, one of the limitations of an augmented matrix is that it does not include the variable names. So we need to actually make it clear what the names of the variables were that we were dealing with. So let's suppose that we're working with the variables x, y, and z, just so we have some letters to use for the variables. So if that's the case, what linear system would this correspond to? Well, we can just convert each of those rows into equations. Remember, the first row is going to be 1 times x plus 0 times y plus 0 times z. So the 0y and the 0z, those won't play any role in the equation, and you'll really just have x equals 2. So I'm going to say which corresponds to x equals 2. That's the equation that would correspond to the first row. Now the second equation would be 0 times x, 1 times y, and 0 times z equals 3. So that would just be y equals 3 because of this 1 here. So the second equation corresponding to the second row would just be y equals 3. And the third row corresponds to the equation 0x plus 0y plus 1z equals 5. So really we would just have z equals 5. So if you take a look at this linear system, one of the things you realize immediately is that there's no work to be done. You don't have to do any detective work to figure out what the solution is to this linear system. It's already solved by the way it's written down. So let's make that observation. This linear system, because it is a linear system, it's a linear system of 3 equations and 3 variables. They just happen to be quite simple. So this is already, this linear system is already solved. So that's an important fact to realize. So our first job is going to be to precisely say, what is it about augmented matrices like this that makes their corresponding linear systems so easy to solve, or already solved, like this one is. So we're going to try our best, and we will be successful in pinning down exactly what it is about this augmented matrix that makes it so desirable. And then that will be our goal when we're solving systems. So we're going to define a couple of terms. So a matrix, so something like this, right? This is a matrix. A matrix is in row echelon form if the following 3 conditions are satisfied. So, and we'll say what the conditions are in a moment, but for now I'm going to underline this, and it's worth making the note that this has an abbreviation. So row echelon form, if you're writing that down, you can save some time by just writing REF in brackets, and that's standard notation. So what are the 3 conditions that it has to satisfy? Well, the first condition says that if you have any rows of zeros, like if there's any rows that in which every entry is a 0, then they must be at the bottom of the matrix. So all rows of zeros must be at the bottom. So that says must be at the bottom. So that's the first condition. And some matrices don't have any rows of zeros. And if that's the case, then this first condition won't apply to them. The second condition says that the first non-zero entry in every row, so and of all the rows that actually do have a non-zero entry, in which the first statement wouldn't apply to them, then if they have a single non-zero entry, then they must have a first non-zero entry, and that had better be a 1. That's what the second condition says. The first non-zero entry of each row must be 1. Okay, and let's just take a moment to check that that's the case up here. So look at the first non-zero entry in each row. And when we say first, we mean starting from the left and moving to the right. So the first non-zero entry, I'm just going to faintly circle them. Here, I've got the first non-zero entry of the first row. Here's the first non-zero entry in the second row, because that one's 0. So here's the first non-zero entry if I'm moving from left to right. The first non-zero entry of the third row is right there. So I've circled all of those, and they are all indeed 1. So they pass the second condition. And the third condition says, roughly speaking, it just says that as you move down, the orientation of the leading ones is that they move to the right. So you can see I have if I were to trace a line under these leading ones, I would be forming a downward staircase to the right. That's really what statement 3 says. And the way you would say it precisely is just that to say the following: each leading one must be to the right of all the other leading ones that are above it. So each leading one must be to the right of every leading one above it. Now, I've actually just started using some terminology here. Leading one. So I'm going to actually tell you exactly what I mean by leading one at this point here. So in property 2, it says the first non-zero entry of each row must be a 1. So the first non-zero entry of a row, that's referred to as a leading entry. And if it happens to also be a 1, then it's a leading one. So when I say leading ones, I'm talking about these. The entries that are the first non-zero entries of their rows and also happen to be 1. So let's squeeze that in here. So these entries are referred to as leading ones. And that's really important. That's a term we're going to use a lot in this section. So that's very much worth making precise. So that's the definition of row echelon form. And you can, as we already did, we can check that this augmented matrix satisfies all 3 of these conditions. And remember, the first condition doesn't need to be checked because there are no rows of zeros. But if there were rows of zeros in this matrix, then we'd have to make sure they're at the bottom if it were to be in row echelon form. So this matrix is in row echelon form.